Alright, okay, so welcome to my presentation. This is going to be on effectively capturing attention using the capture effect. It's joint work with my supervisor Roger Wattenhofer. And let's get right into it. What is the capture effect? Some of you may have heard of this, but I'm just going to quickly go over it. If you have two nodes sending to the same node simultaneously, then in some cases, this does not have to result in destructive interference, and this is a phenomenon called the capture effect. So in this case, these two nodes would be roughly the same distance from the receiving node, and probably both transmissions would get lost. However, if one node is closer to the receiving node and it has a much better link, this will cause the stronger packet to be received without a flaw, and completely ignoring the signal from the weaker link. Now, how much stronger does this need to be? This is just a plot from our system we were working with. On the x-axis you have the difference in received signal strength between the two senders which were sending to the same node, and on the y-axis you have their packet reception ratio. And you can see around 0 here, it's very low, it's very bad, neither packet is likely to arrive, and as you get away from that, it gets better and better for one or the other sender. And this gap, which you can see here, this chasm kind of is 5 to 6 decibel depending on how you want to look at it. There's one more thing which is very important for invoking the capture effect, and that is packet timing. So typically your packet looks something like this. You have a preamble in the front, the start of frame delimiter, a length field, and then the payload. And now, if two packets arrive, and they're not exactly simultaneously, but a little bit off, there may be complications. If the stronger of the two packets comes first, it's no problem, but if it comes later, there might be a problem. So the top one is the weaker packet in this case, and the bottom one the stronger one. In this case, this is not a problem because the stronger packet will override the preamble of the weaker one. The weaker one will not be heard and will not be started to be received. Instead, the stronger one will be received correctly. What you need to know here is that typically a receiver, when it hears a preamble and the start of frame delimiter, it will lock on to that packet and decide to receive that packet no matter what. It will try its best to receive it all the way to the length it has read, even if in between there's some noise. And that's a problem for us in this case because let's say the stronger packet is a lot later. It starts somewhere in the payload of the weaker packet. Now, the receiver will lock onto the weaker packet, and then suddenly the stronger packet will barge in and override these, the data of the weaker packet. And actually, practically both packets are lost because you won't get the data from the first packet. And the second packet will, well, you might get some scrambled stuff here, and then you stop receiving at this point and you don't hear anything anymore. And the critical section is 160 microseconds, which is this part in the beginning. Here's a plot about that. On the x-axis, the delay, how much later the stronger sender starts than the weaker one. And you can see that around 160 microseconds, which is marked here, there's this sharp decline in packet reception ratio for the stronger sender. The weaker sender never has a chance in this scenario. Right, so that was the capture effect. Now, in prior work, we already thought, well, capture effect is a cool thing, we can do some stuff with that, and what we came up with was protocol layering. Essentially, if you have two links to the same receiving node, which are very similar in quality, for example, like this, on the x-axis you can see the transmission power chosen by the senders, on the y-axis the received signal strength at the one receiver, and horizontally indicated here are 4 different values of received signal strength which both senders can achieve through their transmission power setting. And for example, these values here, and they are separated enough to actually cause the capture effect, as we saw earlier. So what does that allow us to do? Well, if something is sent to arrive at the highest signal strength, yes, it will be arrived irregardless of any other packets on lower signal strengths arriving. If nothing arrives on the top signal strength, on the next signal strength something may arrive, and so on. So you end up with these kind of layers where you say, well, if something has priority of layer 4, it will always automatically be received instead of the other stuff. So what this gives you is a kind of automatic prioritization mechanism. And to each layer, it looks as though the network was fully available to it unless a layer further up decides to send, either temporarily, actually both temporarily and spatially close to where the lower layer wants to send. All right, that was prior work, we did that. And now we thought, how about going a step further with this? And in particular, we wondered, what can we do with the capture effect if we try to get rid of this restriction to full packets? So what this prior work also had to do, it had to do scheduling and time slotting. It didn't have to do scheduling. It was trying to get rid of the scheduling. But it had to do time slotting to have packets arrive, well, roughly at the same time, so that within our 160 microseconds, the stronger one will surely be heard. Okay, so now we want to get rid of this. And now if we ignore the packet boundaries, one of the first things that came to our minds was, how about we inject a short packet into a longer packet? Something like this. On top you have the weaker packet here, and below it the stronger packet. The weaker packet is a lot longer, and it contains some latency insensitive data. For example, some bulk transfer of data, and if one packet gets lost, it will be resent. It's no big deal. And the stronger packet, however, is very latency sensitive, and it needs to be sent as soon as possible. It needs to reach whatever destination it has as fast as possible. This could be an alarm packet of some kind, and it's more important that this one gets through than that the weaker one gets through in its entirety. Okay, so we set up kind of an experiment, something like this. Now we want the receiver to receive the string of symbols at the bottom. So these are symbols now, 2 of them forming a byte, but in reverse order. And we want to receive the longer packet until a weaker packet, until the stronger packet arrives, the shorter one, which is down here, and overwrites a part of the payload of the longer packet. And for our example, we just had the longer packet filled with the F symbol, and then in here we have this stronger packet, which has a payload of pairs of 1s, 2s, 3s, and so on, which will be handy to look at in a moment. And then if the receiver actually receives this mixed string of symbols, it can figure out that some packet was injected by looking for the preamble in this packet, so this whole 0 thing, and then the start of frame delimiter, checking the bytes behind this, and then can even confirm with the checksum that this injected packet was properly injected. Okay, so what happens if you just do this naively? That's what we tried first. On this plot you can see, well, on this listing you can see every line is one instance of this experiment, and you can see in black the symbols of the weaker packet, the longer packet, and in blue the symbols which have been altered. And as you can see, none of these cases, and this is just a random excerpt from our logs, we actually managed to receive our stronger packet the way we wanted to. Okay, so what went wrong here? It turns out a symbol is actually not not an atomic unit of transmission when it comes to the physical layer. Instead, a symbol is transmitted as a sequence of chips. And each of the 15 symbols in IEEE 15.4, which we were using, is mapped to a sequence of 32 chips. And for this presentation, you can just assume that these are sent one by one after another. It's a little bit more complicated than that, but that's generally the idea. And one such chip is half a microsecond in length, and the whole symbol then lasts for 16 microseconds. And now when a receiver receives this sequence of chips, it knows, okay, next symbol starts here, it reads these chips and tries to match it the best it can to one of these 15 or 16 strings. And that's where the problem lies, because previously we were trying to just overwrite the whole packet, but that's not an option really, because instead we overwrote some of the chips in the chip sequence. And this was not necessarily aligned very well. Okay, so what we had to do is we had to improve the symbol alignment. We were using the TLOS-B, a commodity, very simple node, also very old by now. It does have a 4 megahertz clock, but that is not very stable. So getting this alignment to work was not very easy. The best we could do was this. We tried to reduce these error sources. The first one being the clock synchronization between two sending nodes, which is exactly what you would think it is. It's the difference in clock between the nodes or their view of the global clock. Then transmission timing, which is once you know what time you want to send, and assuming you have a good clock, to actually be able to send at exact that clock tick you want to. And finally, travel time, which is just a physical problem imposed on us. So if two senders have a different distance to the receiver, their signals will have different travel times, which matters at these scales of time. So we managed to get the clock synchronization down to below 1 tick or a quarter of a microsecond in 75% of cases, with a lot of linear regression and trying to smooth out the jitter. The transmission timing also to below 1 such clock cycle. And the travel time, well, we just said we won't have senders which are more than 10 meters in difference to the receiver. So this restricts this value to be less than 33 nanoseconds. Okay, so if we do all that, what do we get? Okay, now these are aligned a lot better, and you can see we have now some green lines, which are lines in which the injected packet was properly injected, and the symbols actually match 100% exactly what we wanted to get there. But now what about the remaining lines? There still seem to be some patterns here. So for example, this line in the middle here, there's a lot of 5 symbols instead of 0. This seems like something we could take advantage of. If you go to the back here where we have these pairs of symbols, you can see that like 1, 1, 2, 2, 3, 3 translated to, or the other way around, actually 4, 4, 5, 5, 6, 6 translated to 1, 1, 2, 2, 3, 3. So this is clearly something we maybe extract some information from. Yeah, so it turns out there's actually a very simple mapping which works for a lot of these cases, and it is this. So this mapping M just takes some scrambled, let's say, a scrambled symbol S and a constant A between 0 and 7, and then we subtract the last 3 bits, then add the constant on top and put the bits back, essentially. So the first bit always is correct, and then the last ones have to be shuffled a little bit. Okay, and this works very well. Just why is this even a thing at all? So these chip sequences I showed you earlier, they are designed to have a large distance to each other if you know where the symbol starts. So you have the least influence of noise on your decoding phase, on your choosing the symbol phase. And that's true if you know where the symbol starts, but if you do not know where the symbol starts, if you're shifted in this, if you have a long string of chips, just one after another from different symbols, and you start at a random point, then it actually turns out you might not just get some garbage. Instead, the first 8 symbols are actually, the first 8 chip sequences are actually the same, but they are shifted by 4 chips each, and the same for the last 8 symbols. So let me show you this. Here you see the distances between chip sequences and their and the chip sequences you expect. So at the top here, let's say if we're 4 chips late, this whole table is for 4 chips late. If you receive 1 symbol, a string of 1 symbols, but you start interpreting it 4 chips late, then you will find the lowest error to be if you say, well, this is clearly a 2 symbol. And you can see there's actually, for every column, there's a single 0 in here. So this is a mapping we can reverse. We know that if the decoder gave us a 7, and we know it should have been a 0, we know, okay, we're in this case, and it was actually a 6. Wait, that came out wrong. If we know it was a 6, and we got a 7, then we know we are in this case of being 4 chips late. So we can apply this whole table to do the reverse mapping. And that actually just matches exactly this mapping I showed you. Now what if we're 6 chips late? Now this is a little bit troublesome, because now if there's just four symbols, one after another, their chip sequences don't really make a lot of sense. There's multiple candidates even for the closest, like 1, 2, 9, and A. And the decoder will have to choose one of these. And it will just pick some, and we will not be able to revert it because, well, it could have been either. It could have been any of those. And same for the rows, is each row has multiple lowest values. So that's why sometimes we can't do it, even if we figure out how late we are. Okay, so doing all of this, we get a lot more green, very nice. We have still, and we get some actually red values here, which are symbols which were decoded wrong. But there's not a lot of them, so that's nice. And the remaining cases, you can see they're really scrambled beyond recognition. I mean, there's some places where you can say, okay, these are clearly pairs, and then in the front there's something wrong and you can't make it. So we now raised our success rate to about 70%. As a quick overview here, this is about the packet injection, so how often did this work? With no proper synchronization and without this symbol remapping I showed you, we're somewhere around 5%. With the symbol mapping, we can push it up to 30%, and tight synchronization again pushes both of these up a lot to, in the best case, 70%. And the different colors here are, so the blue, as you can see, is that the sync word of the injected packet was recognized as such. So we detected that there was a packet injected and tried to read it. The red one would be that the packet was had at most 3 errors. So as you can see, this is almost always the case. And in, I don't know, let's say 5% of cases, there were no symbol errors at all. In 5% of cases, there were between 1 and 3 symbol errors. So if you can live with these, you can actually get a little bit better here. All right. Now, you can generalize this thought we had here and this experiment result we got here. And if you take away only one thing from this talk, let it be this one. That is that it is definitely possible to decouple the synchronization header from the payload of a packet for a certain price. So you need some conditions to be met for it to make a lot of sense. You need, and even if you have the best conditions, at least in our case, the best conditions for our hardware, we only got up to 70%, but we still managed to get something out of this. So the general thing would look something like this. You have some sender A providing a synchronization header with a long length field, and then other senders can send their data and it will immediately be inserted into the packet at that spot. One more application we thought of, for which this makes a lot of sense, is the crossing of a chasm. So let's suppose you have deployed your sensor node network around some kind of chasm, and you can't put any nodes in the chasm. It's forbidden, you can't do it, it's dangerous. And now the red node over here wants to send to the blue node down here. But unfortunately, all the links across the chasm are of very poor quality. So it's the likelihood that a packet completely without error gets through is completely negligible. So the classical approach would say, well, just do routing and take a path around the whole thing. As you can see, though, that's a lot of hops and that's very expensive. We're not going to do that. And actually, in worst cases, we might not have any connection between the two sides, which relies only on stable edges. Okay, so now with our newfound knowledge, we thought, well, what about putting a node on the receiving side which can send a wake-up header to multiple potential receiving nodes of a packet coming from across the chasm. So the scenario would be this node would know roughly when the red node will send the packet, and then will, before it does, send out a synchronization header with a long packet length to tell all these nodes here that they should start listening. And then they will do their best to record the symbols they get. And then the red node sends its weak packet, and some symbols may come across correctly, others not, and then we hopefully can piece together the full packet from multiple such received bad packets. Would look something like this. First we have a length and a well, we had to put some dummy payload because actually our transceivers wouldn't otherwise let us just cut off the transmission at that point. So we have them send this with a very long length. This is the maximum length for IEEE 15.4. And then afterwards nothing. So the dashes here represent no symbol actually being sent by anybody. So our receiver will have to interpret the noise pretty much. And then, of course, we want to, if possible, get the full packet in here, which was sent from across the chasm. But we know it will have errors because the link is not very good. However, let's say this packet at the top here was sent, then we might receive these 3 packets. And you can see there's not necessarily a lot of errors, maybe just 1, maybe more, but putting these together definitely gives us a better chance of completing the original packet, since these errors appear to be independent of each other, since they occur at the receiver or the receiving stage rather than at the sender. Okay, so what did that look like results-wise? And this is a plot over anything received. So this is just, did the receiving node actually notice there was a packet? So without the wake-up header being sent by our special node, you can see how bad the links were. They managed to, so the blue node at least managed to receive the synchronization header in 40% of cases, which is not a lot, and then these others even less. And you can imagine how unlikely it then is that the full packet will actually not contain any errors. And with wake-up, this is not that spectacular. Of course, this wake-up header is very easily receivable by all these nodes. These nodes will always start receiving. Now a plot over the number of received symbols, or correctly received symbols. This goes from 0 to 58, which was the length of our injected packet. And you can see without wake-up, this is about this quality. So 20 of the 58 symbols were correctly received by our closest node with the best link. And adding the wake-up helped us recover more. And then we can apply actually the same symbol mapping technique again, and you can see this again boosted a little bit. This is still not a lot, but if we put them together, we still might be able to assemble a full packet. Okay, now this, that's maybe hard to read. So this is over the fraction of cases in which a complete copy was able to be reassembled from all of these multiple receivers, putting together whatever they got. And on the x-axis, we have now the transmission power, which of our one sending node. So this is kind of like the width of the chasm. The stronger the transmission power is, the shorter the smaller the chasm is, and the more likely it is that the packets sent by it will directly arrive. And the smaller the transmission power, the wider the chasm, and the poorer the links. So you can see without a wake-up call, this rises very slowly and is still very terrible. It's actually not really usable at all until this point here, where we reach 11 signal strength, 11 transmission power setting. And from there on onwards, these links are stable and we will always receive the full packet at most of these receivers. Now the interesting part, of course, is our approaches here using the wake-up header, and you can see before this point, actually, for these widths of chasm, we actually get something. We actually get a lot. We get up to 30% here. And afterwards, after this signal strength is reached, our approach is not worth it anymore because we have to deal with these scrambled symbols and so on. So our approach really shines in this area in the middle here, and well, you shouldn't use it over here. All right, so future work. So all of this was essentially a bunch of proof of concept experiments which we conducted, and we thought these were quite interesting results, but of course it would be even more interesting to now integrate these new insights about matching your synchronization header whichever way you want into actual Macs. The other thing really we wanted to do is we have not tried it on multiple pieces of hardware and only with this IEEE 15.4 wireless specification. And we only use Telos B so far, as I said earlier. And we believe this should work on essentially any wireless specification as long as your symbols are separated by time and you have this capture effect. So we're kind of hopeful there. All right, so to quickly summarize, the main takeaway is this. You can absolutely detach the synchronization header from the packet payload you want to send. You just have to be aware of the consequences if your synchronization is poor, or maybe if you have a very good clock, you actually want to do this a lot because you will have almost no problems. I showed you some fancy symbol descrambling, which really greatly improved the packet-in-packet example. And I showed you the chasm crossing example, which also turned out very well in this specific case. All right.
We have time for a few questions. So maybe I'll ask you one. So there are a few questions that I have after the talk. Again, I'm not very familiar with this sort of low-level radio hacking, but why is it that when I can actually transmit one hop, which is when your transmit power goes all the way up, why are you failing? Is this because of this one was symbol mapping? And
oh, you're talking about the slow incline here at the end, I guess.
Yeah.
This.
Yeah.
Yeah. As I shortly only mentioned, we have problems because we now have to deal with these not quite synchronized injected packets. So we now have to deal with the fact that we have to do symbol descrambling, and even that won't always help. And really, we lose the advantage of the synchronization header. It's why we usually have a synchronization header. It allows us to know exactly where the symbol should start. So we lose that advantage. So that's why that happens.
Okay, this is Mikko Schmati. This is a good slide to look at. So what if you just use some proper error correcting code on the no wake up case? So have you tried that?
We have not tried that. That's a very interesting thing to do. And actually, we also thought about doing that in combination with our approach, because we also have these cases. Well, most of our symbols are correct, but there's a few off, and we also thought, well, we could put it there. We haven't done it yet, but I think both of these approaches would benefit from this.
Okay, and the second suggestion, you can transmit so precisely, so why don't you send twice with different offsets? So first with this and then maybe two symbols later.
That's absolutely the idea. If you need to have the packet get across somehow, and then we give you, well, this one method has a 5% chance of getting across, this other method has a 30% of getting across, 30% chance, then if you want to reach 100%, you're just gonna do it again until it works pretty much.
Oh, I had a different thing on mind. So, so you said that there is a problem if you are 6 symbol off, right? And you can arrange that you are maybe 6. If you were 6 symbol off, then the next transmission you will be only 2 symbol off. Okay, we can take it offline.
Okay, sure. I mean, I can quickly answer part of it, I guess. I mean, the problem is that our clocks are not good enough. If we didn't manage to hit a multiple of 4 the first time, or even 0, as we ideally want, then we don't actually have a way to ensure that next time we will be better than that.
David Kohler, Berkeley. First, congratulations on the kind of tour de force in executing this so that we can have this playground of all kinds of different packet and this and coding and all the rest, and it's a great enabler. Wherever we are trying to gain an additional capability, often we do this by hurting, in some sense, the narrow peak. We want greater reliability, greater diversity. We pay for it with a richer coding scheme and so forth. And this is another one of those cases. I'm curious, for example, if the packet is in the packet, I have to be able to disambiguate the two. Do you have a sense of where those trade-offs might be? I mean, you've shown we could insert urgent packets into slow packets and so forth. How much would we give in the common case in order to enable these various exceptional cases? Do you have any sense of where that threshold might be?
I mean, I touched on a few of the problems we saw. So as you mentioned, for example, you have to recognize the injected packet, so you can't have the preamble and so on within the normal packet. That's one thing. And then, of course, in this case here, if you are able to get through with a good chance completely without error, then it's really detrimental to try to do this, to do these gymnastics. However, in these cases, I'm not sure we really receive a disadvantage. It's more that we don't rely on the standard case of trying to get the full packet in one go.
But presumably, there's some coding penalty that we pay. This may be a question for us as a community, you know, we pay 10% in the common case because we get this whole long list of exceptional opportunities that have
I
great
see
value.
where this question is coming from. I don't have a good answer, I'm sorry.
Can the next speaker come up? You can ask the question.
Okay, thank you for a very good presentation.
Thank you.
I just want to, basically, given all the filtering you are doing to disambiguate what is packet in the middle, how easy is it for any attacker to, let's say, push its spurious data inside a packet? So,
How difficult it
given
is?
your filtering, the kind of filtering you do.
So, as I mentioned at the start, essentially we need to invoke the capture effect. So we need this 5 to 6 decibel in our case to be able to securely override this stuff. If you have less than that, then your error rate will go up and maybe you will hear the old packet instead. So you have to deal with that.
Okay, I'll ask you question in talk.
Okay, that's
I think we're running over.